This is the third section of groups, chapter 2 from FP2, and we're going to be looking at order and subgroups. Now, before we do that, I think it would be useful to go through some notation. So the first thing is this. So if you see this, this means that I've defined a group called G, and the symbol here represents the binary operation on that group. Yeah, so a different example might be a group that we call H, and this little circle here representing that binary operation. Secondly, if you see these symbols around a letter like that, what we've defined for a group, that means the order of the group, and we'll be talking about that in a moment. So don't worry if you don't know what that means. And here, this is going to represent the order of an element. Order of an element. We'll be using E to represent the identity. And I think that's it actually. So let's start with, I'm going to draw a line going through my work. Let's start by looking at groups and elements. So what are the rules with groups and elements? Okay, so we know that we're going to define a group, maybe using this G or H or S, whatever letters we want, and then a symbol like this to represent the binary operation. So first thing we can talk about is the order of a group. Now the order of a group is basically the number of elements in the group. So the order of a group is the number of elements in the group. Number of elements in the group. Not sure what's happened to the word elements there. Let's try that again. So for example, if I defined a group that had these elements in, then the order of that group would be 4, because it's got 4 elements in it. Now, that means that the order of a group can be finite or infinite. Okay, so the order can be finite, just like the example we've given above, because there's a finite number of elements in a group, or infinite or infinite. So e.g., if my group was defined as the set of positive integers, that's an example of an infinite group. Or maybe a set that was defined as the multiples of 7, the positive multiples of 7 or the negative multiples of 7. These would be example of infinite groups that would have an infinite order. So now let's look at the order of an element. Now, just like the order of a group, the order of an elephant, the order of an element can be finite or infinite. So we're going to look at both. Can be finite or infinite. So let's start with elements which have a finite order. Now let's say an element has a finite order m. Okay, so the order of A would be m. Where does m come from? Okay, this is where m is the least positive integer for which AM equals E. Okay, so basically, let's say A4 was E, then the order of A would be 4. So the number of times we need to sort of basically like A1, A2, A3, A4, whatever this number is, and we get to E, that will be the order of A. Now also, if A has a finite order, there will be different powers of A which generate the same element. So for example, it may be, I don't know, that A7 equals A10 equals A13 and so on. So it's basically the same element. So the way that we would sort of write that is that A to a power equals A to a different power. Okay, and we'll just make sure they are different. We'll just say where X is not equal to Y. So for finite elements, or elements that have got finite order, this will happen. It will sort of cycle through a fixed number of elements, and a number of elements it actually cycles through is the order. And also for elements with a finite order, the order of the element, let's call it A, divides the order of the group, divides the order of the group. So writing that using the notation, we could do this. Okay, so the order of A divides the order of G. So for example, if we had a group that had, let's say, order 10, then the order of the elements within that group could only be order 2, which would be self-inverse. Okay, so we'll write that down. If you've got an element that's got order 2, it must be a self-inverse, because it's just going to create itself, and then the identity itself, the identity, and so on. Or order 5, because they're the only numbers that divide 10. So if a element has a finite order, the order of that element always divides the order of the group, no exceptions. So for example, if you had a group that had order 12, you could not have within that group an element that has order 5, because 5 does not divide 12. Okay, so now let's briefly look at elements which have an infinite order. Infinite order, let's just sort of underline it so we can see where we're going from one thing to another. So if an element has an infinite order, that means that you will never be able to generate the identity. So that's basically what this means here. Okay, so you can never generate the identity, because the whole point with a finite order is that you generate the identity, and then the next element you're going to generate is going to be the element itself. You're going to cycle round, and that happens because you get to the identity. If you never get to the identity, you're never going to cycle round. So obviously you're only going to get elements with an infinite order in infinite groups. You're not going to get them in a finite group. Now, before we said that, you know, you can have these different powers and create elements that have the same, basically the same value. If you've got infinite order, that's never going to happen. So for different powers of Y, I'll call them powers, okay, they're never going to be the same. You're never going to get these two different powers generating the same element. So again, this is where X is not equal to Y. And then lastly, to do with groups and elements are generators. And if we have element that's a generator of a group, its order will be the same as the group. Okay, so if A is a generator of a group, so remember a generator basically generates all the elements in a group. So if A is a generator of a group, then the order of that element equals the order of the group. So the last thing we're going to look at now are subgroups. And subgroups are like mini groups within a bigger group. Okay, they sort of do the same sort of thing, but with a smaller number of elements. So because these things are like mini groups within a group, it means that they're closed. They have an identity, and our identity will be the same as the main group. So same as main group. They'll have an inverse, or every identity will have an inverse, and they'll have associativity. Okay, so they'll be associative. So as I said, these are like mini groups within a group, and quite often we'll use the letter H to represent a subgroup, and like G to represent the main group. Now, because a subgroup is like a mini group within the main group, it actually contains elements which are a subset of the main group. And every group has at least two subsets. So write this down. So every group has at least two subsets. So we're not talking about subgroups, we're talking about subsets. Okay, and these are going to be non-empty. So we're not talking about the empty set, yeah, which we've sort of talked about before. So one subset of a group is actually the group itself, okay, the whole group. And one other subset is what we call the trivial set, and this only contains the identity. Okay, so we call this the trivial set, and quite often you're asked about the non-trivial sets, and that's every other subset. Okay, so any other subset is called non-trivial. And actually some of these subsets are going to form subgroups. Right, let's clear some of what we've got off here and finish off our definitions for these subgroups. Right, so I'm going to be using the letter H to stand for a subgroup. So this is going to be something where I've got some elements that is a subset. So I've got some of the elements of the main group, and they actually form a subgroup. So that group of elements is closed under the binary operation. They have the identity in that group, which is the same as the main group. The elements have an inverse, and the associativity rule also holds. So we've got a little bit of notation to go through. So if we see this sort of a C sign and a line underneath, it's a little bit like less than or equals to. And with G, okay, it basically means that H is a subgroup of G. Okay, H is a subgroup of G. Now this little line at the bottom here means that this subgroup could actually be all of the elements of G. So this includes the group itself. So that's a sort of subgroup. We've talked about that before. Okay, that's actually a subset. It's also a subgroup. So this little line down here says that actually we can include the whole group as one of a subgroup, and then we can sort of look at the order of these. Now this rule also goes on to say that, or this definition, that the order of the subgroup can be less than or equal to the order of the group. And why it's equal to? Because this subgroup may actually be G itself. Okay. Now, if we change the notation slightly, and we have just this rounded symbol like this, okay, H is now what we call a proper subgroup of G. Proper subgroup of G. Now this does not include the group itself. So this little symbol here without the extra line, it means it does not include the whole group. So that means that the order of H is always going to be less than the order of G. The order of the subgroup is always going to be less than the order of the main group. Now, a subgroup can have a generator, and we use this notation here to show that our element A is a generator of a subgroup. So what this means is A is a generator, let's put that in quotes, of the subgroup. So that's how we write it, with those less than, greater than sign either side of it. Now, if H is a finite subgroup, so it's a subgroup with a finite number of elements, you can have infinite subgroups as well. Then the order, let's write it in as a sentence then, the order of H, the subgroup, divides the order of G. So we would write that as, we can write it like this. Okay, and this is called Lagrange's theorem. So if we're going to use this rule, we'll say by Lagrange's theorem, this statement is true. And lastly, a quick way of checking to see if a subset is actually a subgroup is, all we need to do is to check to see if that set is closed. Okay, so we can quickly check. If H is a subgroup of G by seeing if, or checking if H is closed. That's all we need to do. We don't need to check for anything else because it's going to have the identity in it, and these other rules will follow as well, inverse and associativity. So just by checking that a subset of a group is closed, it will quickly tell us that what we have is a subgroup. Okay, so here it says we've got this group G, and here's the binary operation. It's a finite group. Prove that every element in G must have a finite order. Now, the way we're going to prove this is we're basically going to say that we've got a group with order n. Okay, and we're going to say that this group G G has n plus 1 elements. G has n plus 1 elements, and we're going to go on to prove that actually 2 of the elements must be the same. Okay, so 2 elements must be the same, which means that all of the elements in that group must have a finite order. Yeah, because one of the things we said was this, that elements that have a finite order, this rule holds for x not equal to y. Yeah, so it's like a proof by contradiction. So the first thing we're going to say is let G have order equal to n. Then we're going to say let the elements in G be, let's write it down as A2, A3 up to AN plus 1. Now, since we've been told that G is a group, okay, that means that G is closed. Okay, so since G is a group, which we've been told in the question, it is closed. That means, therefore, G has only n elements in it, but we said that there's n plus 1 elements here, so that must mean 2 of them are the same. So it follows that 2 of these elements must be the same. Now, since we used x and y over here, let's do the same. So for example, we would say our 2 elements ax equals ay. Now this is for x not equal to y. Now let's also say that y is greater than x. Now, since we've been told this is a group, then it means that every element has an inverse. So the inverse of this would be a minus x, a to the power minus x. I'm going to do that to both sides. So I'll have ax, a to the power minus x, and then I'll do the same to the other side, like this. Okay, since I've just combined an element with its inverse, I suppose really I should be putting like a little circle here to show that I'm doing a binary operation. This just makes E, and I can combine the powers here and write this as A power y minus x. Now what does this tell us? It tells us that this has given us the identity, so it means that the order of A can be y minus x. There may actually be a smaller power here that gives us the identity. So we're going to say that the order of A, it could be less than, it could be equal to y minus x. There may be exist some other values that also give me the identity, smaller values, but it can't be any greater than this. Now what's this y minus x? Well, they're integers. It's a finite value, isn't it? It's a finite value. So what does that tell us? Well, that because we've proved this algebraically, any element in the group will have a finite order, because I can apply this to sort of any element, apply this process here. And also because we've said that y is greater than x, when we do this, we're going to get a finite value. Okay, so we'll just finish this off by saying, since y minus x is finite, every element in G, and G has a finite order, has a finite order. So if we've got a finite group, then every element is going to have a finite order. It can't have an infinite order. Okay, so here it says, for each of the following groups, write down the order of the group and the order of each element in the group. So let's start with A. So the order of the group is easy. So that's just the number of elements in the group. So that's 4. Order of group equals 4. Now we need to find the order of every element in the group. Now remember, the order of the elements must divide the order of the group. So these elements are going to have either order 1, 2, or 4. They can't have order 3, right? So let's start with 1. So let's start with 1 here. So obviously this is complex multiplication. So when we start, we get 1, then 1 squared is going to give me 1 times 1, and so on. It's just going to generate 1, is it? I'm not going to generate any other elements. So the order of 1 is 1. Okay, let's now look at the second element, negative 1. So obviously you just get negative 1, so that's order 1. So then negative 1 squared, so that gives me 1. And then I have 1 squared. That will give me, sorry, negative 1 cubed. Not sure what I'm doing here. Well, I'll do what I'm doing. So negative 1 cubed. That will give me negative 1, and then negative 1 power 4, back to 1 again. So you can see what's happening is you're just generating 2 elements here. So the order of negative 1 is 2. So let's move on to the I. I suppose this way gets a bit more interesting. So obviously we just get itself I squared. That's going to give you negative 1. I cubed. Well, we just take the negative 1, multiply it by I, so that gives you negative I. And then I to the power 4, so that gives you negative I times by I, which is negative I squared, which will give you 1, and then I5. Well, that takes us back to I again. Okay, so because when we get to here, basically we go back again. I suppose we could do the same with the others, couldn't we? We could say, right, this is the looping pattern, whereas this one here, looping pattern is just itself. The order is 4. So the order of I is 4. And notice that for all of these, you may or may not have realized that the identity of this group here is 1. Yeah, when we hit the identity, we go back to the original element. So here obviously the identity, we just go around it, this little loop. Here with -1, when you square it, you get to the identity. Then you go back, you go around that loop. Here with I, is when we get to I to the power 4, we get to the identity. Then we go back, so that's why the order is 4. Then the last one is -I. So we start with -I. So we're basically looking out for when we get to that identity element. It'll be -1, then -I cubed. So if we times the -1 by I, that'll be I, and then -I power 4. That's going to be 1. So we don't need to keep carrying on because we notice, right, this is the identity. So whatever we do, we're going to loop back and end up here. So that tells us that the order of -I is 4. Okay, part B, we want to find the order of these elements here. 1, 3, 7, 9 under multiplication modulo 10. Right, so let's start with the 1. So that's just going to give itself, every time you multiply it by itself, modulo 10, you're just going to keep getting 1s. So the order of 1 is just going to be 1. And that's because 1 is the identity. And we're going to do it the quick way. When we see we hit the identity, we'll stop, and that will give us the order. So 3 squared, that's 9. Under modulo 10, it's still 9. 3 cubed, that's going to be 27. Under modulo 10, that's going to be 7. Now, I suppose what I should do is put like the proper notation with like little 10 down here, and it tells me that I'm doing this calculation modulo 10. So I think this was 3, 9, 7, and then 3, 4. That's 81, so that's a remainder of 1, so that's going to be 1. 1 is the identity under any type of multiplication. So there we go. So that takes us back to the original. So the order of 3 is 4. What's the next one? 7. So that will give us 7 to start with. 7 squared, 49. Whoops, squared. I think I'm going to need a calculator for cubed and power 4 if I get there. That's going to be 49. So under modulo 10, that's 9. 7 cubed. Right, let's work this out on our calculator and see what we get. That's 343, so that's remainder 3. 7 to the power 4. Let's see what this is. 7 power 4. 2401. So that's 1. Okay, right, 1's the identity. So there we go. Get back to there. So the order is 1, 2, 3, 4. So the order of 7 is 4. So we're now just down to the last one, which is 9. I wonder if this is going to be 4 as well. So that's 9. 9 squared, I know that one. 81, so that's now 1. 9 cubed. This is where we go for our calculator. 9 cubed. 729. So this is 9. Actually, I could have stopped, couldn't I? Because that's the identity there. It's just going to go 9, 1, 9, 1, 9, 1, 9, 1. Like that. So the order of 9 is 2. So before we go on, let's have a look at the order of these elements. So in question A, the order of the group was 4, and the order of the elements was either 1, 2, or 4. They all divide 4. 1, 2, 4. In part B, the order of the group was 4, and the order of the elements also divided 4, so 1, 2, or 4. So we've got a group here that's got these elements under multiplication. Multiplication is here. That's the binary operation, where E is the identity. I can see E is in the table. Yeah, that's the identity. You can assume the associativity axiom is satisfied. That may be useful later on. And we've got this partially completed Cayley table, which we're going to be completing in a moment. And the first thing we need to do, part A, is state the order of the group. Now the group has 8 elements, so the order is 8 since G has 8 elements in it, so that's nice and easy. Part B, we want to state the order of 2 of the elements, P and Q. So let's start with P, and let's have a look. So we've got P here. We're going to multiply by the identity, so that would be like just like first order, second order, third order, so fourth order. Yeah, it's like the fourth one in the table. We apply P to itself, and on the fourth time of multiplying P by itself, we'll get E. So the order of P is 4, and we need to find the order of Q. So let's look at Q. Q is here. Right, can you see that Q is just here? I only apply it to the identity. And it's got Q. Let's keep going. Right, here we go. So Q multiplied by itself gives me the identity. That tells me that Q is self-inverse and its order is 2. Any element that's self-inverse has an order of 2. Okay, part C, what we've been asked to do is to copy and complete the table. Well, the table's already here, so I've got nothing to copy out. It's just completing the table. Now, when we complete this table, we need to be careful, because when we multiply, remember that it's this we multiply first, multiplied by this second. Yeah, so it's always the column multiply the row, and that order is important. We cannot assume that the multiplication here is commutative. That means we cannot assume, for example, that P times Q, that would be this, is equal to Q times P. And actually, if we have a look, P times Q is PQ, but Q times by P is P cubed Q. These two are different, so it's not commutative. We can't change the order, and that's really important. Yeah. And the second thing is, when we fill in these, we need to use the calculations that we already have here to help us fill in these elements that go in here. Okay, and you'll see that in a moment. So let's start with this box here. So that's going to be what we get by doing P cubed times by PQ. Okay, so let's just write this down. Let's just write working. So this first box here that we've got in green, so P cubed times by PQ. Now from the table, PQ, where do I find PQ? PQ is here, is actually P times Q. So I can write this as P cubed times by P times by Q. We've been told that the associativity axiom is satisfied, which means I can change the order in which I multiply. I can multiply these two first. And if I do that, what I'll get is, well, I need to check what P cubed times by P is. The temptation is to write P to the power 4, but look at the table. P cubed times by P is E. Okay, so I'll write down E times by Q. And since E is the identity, we just end up with Q. So we can put Q in this box here. Okay, we'll do a few of these and then I'll actually just finish off the table. Won't go through every single one. Okay, let's have a look at this one here. So in that box, what we've got is p cubed, let's get to black, p cubed times by p squared q. Now, the solution to this isn't in the table, p cubed times by p squared q, so we're going to have to use the table to help us work it out. So the first thing that we notice is that this p cubed that we have here, p cubed is p squared times by p, so we'll rewrite p cubed as p squared times by p times by p squared q. Now we can work out this bit here, p times by p squared, again using the table. P times by p squared is p cubed, so what I have is p squared times by p cubed q. Now that's useful because I can use the table to work this out. So p squared times by p cubed q is this, pq. Yeah, so I've changed it into a multiplication that is in the table. P squared times by p cubed q gives me actually just pq. So this is equal to pq. So I can put pq in the table. We'll do one more before I just fill in the rest of the table. So this is so you can get an idea of how this all works. Okay, so this multiplication is going to be p cubed times by p cubed q. So let's write that down. P cubed times by p cubed q. Right, so we're going to do something similar to what we did on the last calculation. Is start with this p cubed. P cubed is equal to p times by p squared, or we could use p squared times by p. Now we can write it either way, we'll end up with the same answer. So I'm going to write this as p squared times by p. So what we'll have now is p squared times p cubed q. Now I can work out this from the table, p times by p cubed q. P times by p cubed q just becomes q. So that bit I've underlined in red just becomes q. So I've got p cubed times, or p squared times by q. And again from the table, p squared times by q is just p squared q. So that will go in this cell here, p squared q. So can you see we're always referring back to the table? We're not just saying, oh, using rules of algebra, because it looks like multiplying things like, you know, like we would in algebra. You've got to be very careful. Don't be tempted just to sort of see things like this and think, oh, right, I'll just add the powers, that's going to work. We must always refer back to the table. So now I'm going to complete the last 12 cells. Okay, so there's the completed table. We just need to do the last bit of this question here, part C, which is verify that it forms a group. So we need to check that it's closed. We need to check that there's an identity, an inverse, and, well, associativity has been assumed, so we don't need to worry to do that. So the first thing we're going to do is to check to see whether this group, or whether this set here is closed. So looking at the table, there are no new elements here that don't occur in the columns and row. Okay, so the original elements there all appear in the table. There aren't any other elements. So the first thing we're going to write down is that the or G is closed. We can see that because there aren't any new elements. Okay, so G is closed since there are no new elements in the Cayley table. So that's the first thing, it's closed. Second thing that we need to check for is identity. Well, we've been told the identity is E. We need to check for inverse. So all we need to do is to check that E appears in every row and column. So let's maybe highlight the E's in red. Right, so there's one in that column, one in that column. If we can find an E in every row and column, then that tells us that every element has an inverse. And yes, there is. So going across every row has an E in it. Every column has an E in it. Okay, so we can just write down since in black. So since E appears, or the identity appears in every row and column, every row and column, every element has an inverse, every element has an inverse, and associativity is assumed, isn't it? So we'll just put associativity is assumed, therefore G is a group. G forms a group. And we'll just go on to part D, and we want to find the orders of some of the other elements. So we'll start with finding the order of PQ. So here we've got PQ. Where does E occur? When we multiply PQ by itself, so it's self-inverse. So the order of PQ is 2. We'll have now a look at P squared Q. So P squared Q is here. Again, it's self-inverse. When we multiply it by itself, we get the identity. So the order is 2. And then the last one, the order of P cubed Q. So again, looking at the table, P cubed. Right, there we go. It appears here. So again, the order is 2. And although the question doesn't ask it, all of these elements here are self-inverse. Any element that has an order of 2 is self-inverse. Okay, it says here that we've got this set 0, 1, 2, 3, 4 forms a group under addition modulo 5. Explain why no element of this group other than the identity can be self-inverse. Okay, well the first thing is if an element is self-inverse, it has an order of 2. But one of the rules says the order of an element must divide the order of the group. Must divide the order of the group. Okay. But 2 does not divide 5, does it? So therefore, no element can be self-inverse using that rule that the order of an element must divide the order of a group, and 2 does not divide 5. Okay, in this question here we have an infinite group, and it's the group of 5 to the power of an integer. So remember, these integers can be positive or negative. We want to show that it forms a group. Okay, so first of all, we need to check for closure. Right, so since we're looking to see if it forms a group under multiplication, basically what we need to show is that if I do 5 to any power times by 5 to any other power, or any power, I'll get 5 times a power. Okay, so the first thing we're going to do is say let a and b be an integer, and then what we'll have, we can say 5 to the power a times 5 to the power b. Well, using the rules for powers, what do? We add the powers, okay? And a plus b is also going to be an integer, so therefore S is closed. Second thing we want to check for is the identity. Now with multiplication, the identity is going to be 1. How can we get 1? And that's going to be by multiplying by 5 to the power 0. Okay, so the identity is 5 to the power 0. It's like multiplying by 1. Next thing we want to look for is the inverse. What can we multiply to give us 5 to the power 0? So again, if we say A and B are going to be these integers, then if we've got 5 to the power A, actually I didn't need to do B, I could have just done A. Let's do that. So let's just have A, that's all we need. So A is an integer. If I do 5 to the power A and multiply it by 5 to the power of negative A, I get 5 to the power 0, so I get the identity. So this is going to be true for all A. Okay, so true for all values of A. So then we can say therefore every element has an inverse. Every element has an inverse. Now in this one, associativity isn't assumed, so we need to check for it. Is this group associative? Okay, so let's have A, B and C. B are integers. Now if I do 5 to the power A times by 5 to the power B, let's put this in brackets, times 5 to the power C. Using our rules, that's 5 to the power A times by 5 to the power B plus C. Then we can use my rule for that, 5 to the power A plus B plus C. And to check for this associativity, we're now going to do 5A times 5B times by 5C. So that's going to be 5 to the power A plus C times 5 to the power C. So we get the same thing again. Okay, so associativity holds. Associativity holds. So we can then say, therefore, the set S forms a group under multiplication, but we don't need to write that down. Okay, part B, what we want to do is determine whether each of these subsets of S, again under multiplication, forms a group. So we're going to be checking group T, where T is the set of integers or powers of 5 to the power of 2n, where n is an integer. Right, so is the group closed? Well, if we use the same A and B as integers, I'm not going to write that statement out again, you see them up here. 5 to the power 2a times by 5 to the power 2b will give me 5 to the power 2a plus 2b, which we can write as 5 to the power 2a plus b. So it's closed because it's of the same type, isn't it? 5 to the power 2 times an integer, and a plus b is an integer. Okay, so now let's look to see if there's an identity. Okay, so the identity is going to be the same as before. The identity is going to be like multiplying by 1. So 5 to the power 2 times 0. Okay, that's of the same type, so we've got an identity. Inverse. Well, if I've got 5 to the power 2a and I multiply it by 5 to the power 2 times by negative a, so it's always got to be of the type 5 to the power 2 times something, that will give me 5 to the power 0. So we've got an inverse for every element, and we'll just check for associativity. So associative in the space that we've got down here. So we'll have 5 2a times 5 2b times 5 2c. Okay, I'm going to put the brackets around these two first. So that'll be 5 2a times by 5, and then remember we add the powers, so it's 2b plus 2c, and that leaves us with 5 2a plus 2b plus 2c. Now we can see that actually if we put the brackets around here, so I'm not going to write all the working out, okay, it will also, I'll also get the same result at the end, but I'm not going to write all of it out. You can see that it's fairly straightforward. So this group, or this set here, T forms a group. T forms a group. Right, so now let's look at U. And U is 5 to the power n, but this time n is a positive integer. Now what that means is n is going to be not 0 but 1, 2, 3, 4 and so on. So there's a couple of ways we can show that it's not a group. Firstly, there's no identity. No identity, because the identity is 5 to the power 0, and there is no 5 to the power 0. So no 5 to the power 0, because 0 is not a part of n. Also, we could show that there's no inverse as well, because there are no 5 to the power of negative n. Yeah, because n is positive. So there's two ways that we could show that U is not a group. So U does not form a group. And this is an example in this question of an infinite group. I don't know if I've mentioned that before. This is an infinite group. Okay, so here we've got a set from 0 to 7 that forms a group under addition modulo 8. Find two non-trivial proper sets of S modulo 8. So the first thing we're going to do is to construct a table. It's under addition modulo 8. And let's write down the elements here. So 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. So let's straighten that line out a bit. And let's now fill this table in here. Okay, so here's our completed Cayley table. And it's important to note it says two non-trivial proper subgroups. So non-trivial means that we can't have the set that's just got the identity in. Okay, so no identity subgroup. And in this case, with addition, the identity is going to be 0, so we can't have a set just with 0 in. Okay, it is a subgroup, but that's a trivial subgroup, so we're not allowed that. And it also says proper subgroups, so we're not allowed the subgroup that contains all of the elements, yeah, because that is a subgroup, but it's not a proper subgroup. So these ones are not allowed. Yeah, so we want to find the others. Now the first thing to note, we know that the order of a subgroup, of subgroups divide the order of the group. Divide the order of a group. So that means that our subgroups must be order. So how many elements have we got? 1, 2, 3, 4, 5, 6, 7, 8. Our subgroups need to be either order 2 or 4. Yeah, 1 is going to be the identity subgroup. Okay, we're not allowed that. And 8 divides 8, but that's not a proper subgroup. So the only other subgroups that are left are 2 and 4. Now the easiest way to find subgroups is to go through each of the elements, and what we want to do is to see what it generates, yeah, and see what each element generates, and they're either going to generate one of these groups here, or they're going to generate a different subgroup. Okay, so let's start with 0. Now what does 0 generate? Well, if you just keep adding 0 to 0, keep adding it to itself, that's just going to generate the trivial subgroup. So we'll go on to 1. What does 1 generate? Remember, this notation means that it's a generator of a group. So if we just keep adding 1, we're going to get 1, 2, 3, 4, 5, 6, 7, and then back to 0. So 1 generates the whole group itself, so that's not a proper subgroup. Okay, let's go on to 2. What does 2 generate? Well, that will be 2, and then 4, then 6. The next one will be 8, so we'll get back to the identity 0, and then back to 2, 4, 6, 8. So 2 is a generator of this subgroup of order 4. So this is 1. Okay, so we'll stick a tick by that. That's 1. Let's move to 3. What does 3 generate? So we'll have 3, 6, and then 9 will be 1, and then 4, 7, 2. So I'm just working out a remainder because 7 plus 3 is 10. Next remainder 2, then 5, and then 0. So actually 3 generates the whole group again. It generates S. So that's not a proper subgroup. Let's move on to 4. What does 4 generate? Well, 4, and then add 4, 0, and then back to 4 again. Okay, so this is a proper subgroup of order 2. And 5. What does 5 generate? So 5, and then add 5, 10, remainder 2, and then 15, that would be remainder 7, 20, that would be remainder 4, 25, remainder 1, 30, that would be remainder 6, where are we? 35, remainder 3, 40, okay, to the identity. So that generates the whole group. 6, do the same thing again. What does that generate? So 6, and then 6 plus 6 is 12, so remainder 4. And then 4 plus 6, 10, remainder 2. 2 plus 6, 8, right, the identity. So that's a subgroup order 4. And last one, 7. What does 7 generate? So 7, then 14. So that's remainder 6, then 21. So that's remainder 5, 28, remainder 4, 35, remainder 3, where are we? 42, that'll be remainder 2, 49, remainder 1, and then 56, right, no remainder. Oh, look at that, it actually generates this group going like this. It's interesting. Again, this is not a proper subgroup, so what do we have to finish with our subgroups are 2, 4, 6, 0. So that is has an order of 4, and its generator is 2. And then we have the other subgroup 6, 4, 2, 0, and that has a generator of 6. And then lastly we have that subgroup of 2 elements, which has a generator of 4. So notice that the order of the subgroups divides the order of the main group here. Okay, so we've got this group G here that's got 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12 elements in it. So the order of G is 12. That might be useful. And it forms a group under multiplication modulo 21. Okay, so we can write that when we work out our answers, we'll write this down. So part A, find the elements of the subgroup generated by the element 5 and state its order. Right, so what does 5 generate? Right, well the first one's going to be 5, because we know that 5 in modulo 21 is just 5. Next one, because it's multiplication, is going to be 5 squared, which is 25. And 25 in modulo 21, that's easy, is going to be 4. So let's write down the next element. Next one is 5 cubed. So that's 125. So what's 125 in modulo 21? Well, let's have a look. 125 divided by 21 gives me 5 point something. So let's try 5 times 21. 5 times by 21, that's 105. That leaves a remainder of 5 there. So, oh sorry, no, it's 105, isn't it? 105, it's a remainder of 20. Maybe I should write down the little calculations here. Yeah, let's write down that 5 times 21 is 105. So I don't make that mistake. So yeah, the next element is 20. Then we have 5 to the power 4. So that's going to be 625. So what's 625 in modulo 21? Let's have a look. So 625 divided by 21 is 29 point something. So now I'm going to do 29 times by 21, which is 609. So I'll do that here. 29 times 21 is 609. So I can see 625 minus 609 leaves a remainder of 16. So let's write that down, 16. So that's the next element that's generated. 5 to the power 5. So that's 5 to the power 5 is 3125. Right, so what's 3125 in modulo 21? So 3125 divided by 21 is 148 point something. So now we'll work out what 148 times by 21 is, so we can get the remainder. 148 times 21 is 3108, 3108. So 3125 minus 3108 leaves a remainder of 17. So 17, so that's the next element. Now we'll do 5 to the power 6, which is 15,625. Let's work out what this is in modulo 21. So let's divide that by 21. And we get 744 times by something. So now I want to work out 744 times by 21. 744 times 21. And that's 15624. 15624. 6, 2, 4. Okay, so that's going to have a remainder of 1. Right, in multiplication, in any modulo, 1 is going to be the identity. Now remember, when we've got to the identity, what's going to happen next is we're going to go back to the very first element that we have generated. So I will get 5 again. Now I know that's going to happen, but just to prove it to you, let me work out 5 to the power 7, just to show you. Now you wouldn't need to work this out, but just to show you get back to 5. This is 78,125. So let's work out what 78,125 is in modulo 21. So I'll divide that by 21 and I get 3720 point something. So let's work out 3720 times by 21. 3720 times 21, and that gives me 78,120. So I can see that's a remainder of 5. So I've gone full circle. I'm back to the 5 again. So 5 will generate 1, 2, 3, 4, 5, 6. So the order of this subgroup is 6. I don't know if I said 5, I meant 6. 1, 2, 3, 4, 5, 6. Okay, so the order of the subgroup is 6, and we'd expect that because 6 divides 12. Yeah, we wouldn't, if we got a subgroup of 7 or some other number that doesn't divide 12, we know we've made a mistake somewhere. And part B, explain why this group has no subgroup of order 5. That's because 5 does not divide 12, and that's Lagrange's theorem, isn't it? Okay, so since 5 does not divide 12 by Lagrange's theorem, and we should really state that when we use it, there is no subgroup of order 5. So you should now be able to do exercise 2C on pages 69 to 72. I'm not going to recap everything that I did at the beginning, just one or two things, what I think are the important things. So we need to know subgroups, what is meant by trivial and non-trivial subgroups. So trivial, non-trivial. Also what is meant by a proper subgroup. When you've got a question and you need to fill in a Cayley table, it's important the order matters. So don't assume that A star B equals B star A. Okay, it may be that they don't equal each other. And also with a Cayley table, if you're asked to fill in the Cayley table, make sure that you use the calculations or use the answers in the table to find new answers. Don't be tempted to just look at it and look at some patterns and think, oh yeah, I can work out what's going to fill in the table. You can use use generators to actually find subgroups. So use generators to find subgroups by Lagrange's theorem. This tells us that the order of a subgroup divides the order of a group. The order of a subgroup divides the order of a group. And lastly, one quick way to check if a subset is a group, all you need to do is to check that the subset is closed, and that will prove that it's group. Okay, so to prove a subset is a subgroup, you only need to check for closure. You don't need to check for an identity, because the identity of a group will be in the subgroup. You don't need to check for inverses, because you'll find the inverses of the elements in a subgroup that just follows. And you don't need to check for associativity either, because if the group is associative, the subgroup will also be associative.